Hi, everybody. So I'm Peter Pietzuch from Imperial College London. It's my pleasure to talk about the work that we've been doing at Imperial to better support compute-intensive applications in cloud environments. So this work was mostly done by my PhD student, Segarra, who's the first author here on the paper. But unfortunately, he couldn't give the talk because he didn't get his visa in time. So instead, you're stuck with me here. So the focus of this work were compute-intensive applications. So these kinds of applications you'll find in a lot of domains, right? So think of sort of classical high-performance computing applications, weather forecasting, physics simulation, and these types of things. And more recently, machine learning applications, since they need to exploit parallelism, also fall into this class. So because of the high compute demand of those applications, they are typically deployed in large clusters. Sort of traditionally, we've used on-premise clusters with dedicated servers, but now increasingly we're using virtualized cloud infrastructure where we're deploying those applications on virtual machines running on vCPUs. So how do we implement such applications? Well, there are sort of various ways of building an application that takes advantage of parallelism. So one is to make it a multi-threaded application, right? So we have multi-threaded application that then have shared memory across those threads. And there are many popular programming models that enable this. So OpenMP is sort of one classical example. But when you look at machine learning libraries such as NumPy, they will exploit multiple threads for parallelism. Obviously, the other way of building such applications is to make it a distributed multi-process application. So now we have processes running on different nodes, and they perform message passing between each other. So MPI is a classical example of this programming model. And when you look at machine learning frameworks, such as, for example, distributed PyTorch, this is what they do to enable distributed training and inference. So why are those types of applications a good fit for cloud? Well, they are a good fit because fundamentally they enable scaling, right? So for a multi-threaded application, we can scale up by allocating a larger number of vCPUs to the threads of that application and thus increase parallelism. And similarly, for multi-process application, we can scale out, so allocate more processes running on further VMs and again, increasing parallelism. So how would a cloud provider support these kinds of workloads when running multi-threaded, multi-process applications? So let's look at an example. So we have a cloud provider and we have 3 VMs, A, B, and C, and the cloud provider needs to schedule particular applications that have a given compute demand in terms of the vCPUs that they would like to see allocated. So application 1 wants 4 vCPUs, so we can allocate it on VMA. So then another application comes along that wants 6 vCPUs, so we can place this on VMB, and so on. So we have another application now using 2 vCPUs on VMC. So if now a further application comes along with a compute demand of 8 vCPUs, well, we can't support this on a single VM, right? So what if this application happens to be a multi-process application, what the provider can do is they can split it up across multiple VMs, right? And they want to do this because they want to achieve high utilization of the resources that they have. So they will keep doing this, essentially allocating applications onto the infrastructure, but this now introduces fragmentation, right? So it introduces fragmentation for those applications because they are now split across VMs and there will be communication over the network, and that then results in worse performance. So cloud users, they want good performance, right? So how can we avoid this problem? Well, one thing that the cloud provider could do, they could delay the allocation to avoid fragmentation. So when this application 4 comes along, instead of immediately allocating it, the cloud provider could wait until application 3 has finished, released its resources, and they could then place all of application 4 on VMC. So now they've avoided fragmentation, but they've reduced the utilization of their infrastructure, right? So that is not what the cloud provider wants. So the question that we've asked is, well, can we dynamically change the allocation of multi-threaded, multi-process applications in a cloud environment to avoid this kind of problem? So this is what we've done in Granny. So Granny is a runtime that enables cloud provider to dynamically manage these compute-intensive applications. And so what Granny supports, it supports adding additional vCPUs to multi-threaded applications. So here we have multi-threaded application 1 running on VMA, the blue one. So we can now vertically scale that application, increasing the parallelism, allocating further vCPUs on that VM when they become available. So the second feature that Granny allows us to do is that we can migrate multi-process applications across virtual machines. So here in this example, multi-process application 3 is fragmented across 2 virtual machines. So with Granny, we can do horizontal migration to then consolidate all of the processes of that application on a single VM. And Granny achieves all of this without requiring modifications to multi-threaded and multi-process applications. And so here we are assuming that the multi-threaded application is implemented using OpenMP, and the multi-process application is an MPI application with message passing. So let's have a look at how Granny achieves this. So the key idea is that we introduce a new execution abstraction that we call a granule. So all applications execute as granules, and granules can execute either with thread or with process semantics. So when a granule is deployed, each granule occupies exactly 1 vCPU. If we now have a multi-threaded application, that application would be represented as multiple granules that run on the same virtual machine, as shown here in blue. If we have a multi-process application, that application will simply have multiple granules that now span several virtual machines, as shown for the yellow application here. Okay? So what are the challenges that we had to overcome to enable this granule abstraction? So the first is, well, how do we unify process and thread semantics so that we are expressing both thread and process state of the application that we're running? The second challenge was around safety. Since we want to dynamically change the resource allocation, so for example, change the parallelism, dynamically add threads to an application, how can we do this safely while maintaining the consistency of the memory that the application uses, right? So if there are, for example, concurrent threads accessing some data structure, how do we ensure that we're not corrupting this data structure as we change parallelism? And then finally, how do we support migration between VMs implemented as the migration of granules efficiently so that we get a performance benefit? So one of the kind of key ingredients that we have for overcoming those challenges that granules use WebAssembly to execute the application. So WebAssembly is a memory-safe intermediate language, and we can take existing application code in a supported language and simply recompile it to obtain a WebAssembly representation. So the reason why granules use WebAssembly, that WebAssembly gives us this really simple linear memory layout for the application. So essentially in WebAssembly, a WebAssembly module is simply a linear range of memory that then contains the stack, the data, and the heap of the computation that is being executed. And so this simple memory representation then enables us to define granules in a way that they can execute both with process and thread semantics. So how do we do this? So all granules that execute on a given virtual machine share a single virtual address space. So if we now have 2 granules that are supposed to have process semantics, what we're simply doing is we're mapping them into separate regions of that virtual address space with separate page mappings. So that gives us the right semantics where they essentially now have both their separate heap. And then any interaction, any IPC that happens between those granules, for example, if they want to exchange messages, this is then handled by our runtime. If we have two granules with thread semantics, well, now they need to share memory, for example, share the heap, and we achieve this through a shared page mapping. And so again, then the runtime manages some of the operations around thread spawning and thread synchronization. When we're spawning a new thread, we, for example, need to allocate a separate stack for that new granule that we've created. Okay, so now that we have a way of representing granules, how do we manage them safely? So the Granny runtime executes each granule as an OS thread, and the granules then interact with the Granny runtime at well-defined control points via API calls. So those API calls are implemented by backends that implement, for example, OpenMP APIs, so MPI APIs, or different POSIX APIs. Right? So whenever the application normally would want to do a system call, it goes via one of those control points and via one of those APIs. So why does this help with consistency? Well, because we can now reason about the granule state at those control points. So an API call could, for example, be a barrier that all threads have reached. So once that barrier has been reached, we know that there will be no further updates to shared data structures at this point, and that means that it's now safe for the Granny runtime to, for example, change the thread allocation. So we can now reason about the fact that there may be no inconsistent thread state or no in-flight messages at that point in time. Okay? So now that we know that a granule is in a consistent state, we can snapshot it efficiently. And here, again, we're taking advantage of our WebAssembly approach, where we know the entire application state can simply be captured based on that linear memory array that we have for that WebAssembly module. And any other state is the runtime state maintained by the Granny runtime itself, for example, messages that are about to be delivered, and that is also something that we can snapshot efficiently. So using that, we can now implement efficient migration of granules, right? So we're snapshotting a granule at a control point, so such as, for example, a barrier join that the granules have reached. So now, at that point, we can make a decision whether we want to migrate a granule, right? So this is now a decision that the cloud scheduler carries out. So if it then decides to migrate a granule, so here in this example from VMB to co-locate it with the other granule on VMA, it can then snapshot that granule and then terminate the snapshotted granule. So now the granule can be serialized and transferred over the network. We can now resume it on VMA, so restore the granule from the snapshot, and then finally resume the execution of both granules at that barrier, ensuring consistency. Okay? So this is sort of the idea behind the mechanism of granules that we have. So what are the management policies that Granny now enables? So in the paper, we discussed three different policies. So one is a compaction policy that looks at this trade-off that I've introduced between utilization and fragmentation. Another one is an elastic scaling policy where we're dynamically scaling up multi-threaded application when extra vCPUs become available. And the final policy is a spot VM policy where we're migrating granules away from spot VMs that are about to be evicted. And we're comparing against various baselines. So one is an Azure batch scheduler, and that scheduler allocates at a VM granularity. So what that means, it would give low fragmentation, but it would also suffer from lower utilization. So the other baseline that we compare against is the Slurm scheduler, and that one would allocate at a vCPU granularity. So that achieves high utilization because it sort of greedily tries to use all of the vCPUs available, but it also introduces more fragmentation. So in the interest of time, I will only talk about the compaction policy. So here, the workload has been a distributed multi-process application. So we use the LAMS molecular dynamics simulator, and we've deployed 100 instances on a 32 VM cluster with 8 vCPUs each. And then we observe job completion time. So this is shown here as a CDF, where essentially things to the left are better. And this shows the CDF that we get of job completion time for the Azure Batch scheduler and the Slurm scheduler. And you can kind of see that they sort of behave quite comparably, because even though they both sort of emphasize utilization versus fragmentation, essentially both of them negatively impact job completion time, so they behave quite similarly. When we now compare this to Granny with dynamic migration, we see that it achieves lower median and tail job completion times. And the reason for this is that it can dynamically shift granules around and therefore remove fragmentation, which helps with overall application performance. So an interesting observation is that we actually had to leave a certain level of headroom where we leave particular vCPUs unallocated so that Granny has enough flexibility to remove fragmentation. So here in this experiment, we ensure that 5% of all vCPUs are left idle to support the migration mechanism. Okay, so with this, so let me conclude. So I try to convince you that there's an opportunity to jointly optimize for utilization and fragmentation when we support compute-intensive applications in cloud environments. And so I talked about Granny as a new runtime that tries to do dynamic management for these types of workloads. And the key idea is the abstraction of granules that works both for multi-threaded, multi-process execution, and it enables new management features such as elastic scaling and dynamic migration of computation. And sort of the way granules achieve this, that they rely on cooperation from the application through control points. Because we know the state of the application at those control points, we can therefore change the allocation of resources in a safe way. So in future work, we're quite interested to look at other types of multi-threaded, multi-process APIs, for example, for machine learning workloads, data analytics workloads, and apply similar kinds of granular management techniques. Okay, so with this, I'll stop. So all of the source code for Granny is available, released as part of the FASM project, and there are far more details in the paper. So I'm happy to take any questions. Thank you.